Hello, everyone. My name is Amanda. I'm a PhD student at the Université du Québec à Montréal. I am currently under the supervision of Drs. Abdoulaye Banire Diallo and Dr. Etienne Laure. And today I'm going to present my talk, which is entitled Precision Farming for Profit, Leveraging Profitability Maps and Integer Linear Programming Management Zoning to Optimize Profit and Soil Conservation of Agricultural Fields. So first, I'm going to give you a quick outline of my presentation. I'm going to start with an introduction where I will define some key terms. Then I'm going to present the problem that we're looking at, a brief description of the materials and methods that we used, our preliminary results, future work that we anticipate to tackle, and conclusions and key takeaways from our short study. So before I begin explaining what profitability maps are, I did want to start with the concept known as site-specific management. And Etienne kind of touched on this a little bit in his talk this morning. But site-specific management is a branch of precision agriculture that aims to determine what we call management zones, which take into account the spatial heterogeneity and temporal variation of agricultural fields. And these zones are delimited using georeference information, which can either be proximal, coming from sources like yield monitors, robotics, or handheld sensors, or using remote sensing technologies like satellite images, drone images, or crop layer maps, for example. And each zone proposes an optimal management strategy for every location on the field. So here's a quick example of this in practice. We have two fields that are shown on the right, and these zones are created by clustering different types of soil properties, like let's say yield, elevation, pH, etc. And we can also see from the figure that the field configuration changes considerably depending on the number of zones that we're looking at. And we can also see that these zones can have what we call undesirable characteristics. Like, for example, they can be non-homogeneous, they can be fragmented, and also have irregular shapes. And these are all challenges when we want to apply these zones into practice and make them compatible with agricultural machinery. And another thing that we need to take into consideration is that multi-year data is preferable to delimit management zones. And this is because agricultural fields are continuously subject to variable conditions like changes in weather, the occurrence of pests, etc. And having multi-year data helps to account for these uncertainties. And finally, yield data that comes from different crops, in the specific case of using a yield map to delimit management zones, they cannot be compared or combined, which creates a challenge for evaluating fields that undergo processes like crop rotation. So here is where the concept of profitability mapping comes in. So profitability maps can also be used to derive management zones, and the neat trait about them is that they have a common unit, which is dollars per hectare. And this is irrespective of the management strategy that we've used, the crop planted, or the year that we're looking at. So in consequence, they can efficiently be combined or compared with each other in a multitude of ways. And multi-year and multi-crop maps can be created, like as I show in the figure. So we can have a map that shows all the years of a specific field that was under, let's say, that was planted with soybean, or all the years where we planted corn, and combine these all to give a global overview of how the field performed in those circumstances. And another thing that we can use profitability maps for is to identify areas that are prone to remain unproductive over time. So here comes the problem that we'd like to tackle in this case. So if we look at traditional methods to define management zones, they commonly use data that shows only a single time step. And they look at soil attributes like organic matter, soil pH, soil texture, which are all important attributes, but sometimes these attributes are not what the farmer is really interested. Usually the farmer is interested in how much he's going to return in that growing season or over the course of the field's lifetime. And this presents multiple research opportunities that we can then look at. Like, for example, traditional methods produce zones that are not really applicable in practice in some cases, like I showed before. And farmers also have huge records of yield data in some cases, which are often not exploited because they lack the available expertise or the time to go back and actually look at this data with all the stress of the season, of the growing season. And few studies have attempted to produce profitability maps and zones, even though it has been shown that they can be very beneficial to farmers. So therefore, the question that we wanted to investigate in this is, how can we exploit the information that's contained within profitability maps to create practical management zones? This means zones that we can actually apply in a real setting. And what we looked at to achieve this is a particular zoning method that the unique trait about this method is that it enables us to create rectangular zones. So rectangular zones are are more convenient to use with current agricultural machinery. And it's a zoning method that's designed as an optimization problem, where you try to minimize the sum of the variance in a given field rectangle that we propose, and you also constrict the number of zones that you generate within a minimum and maximum. And here's a little figure that shows an example of this. So we have a thematic map showing a symbolic field, and what we do is we try to divide the field into different management zones, where we try to prioritize the creation of zones that are homogeneous. And in our case, we attempted to reproduce this method. However, we did change it slightly. Here, because in the previous method, you have to calculate the variance of each rectangle before running the program. This can become extremely computationally expensive if the field, as the field grows. So in this case, we try to approximate the variance by using the maximum of the value within a proposed zone minus the minimum. And the other constraints remain the same. So the number of zones generated is limited between two values, and every point on the field is covered by one unique zone. And if you want to give more specifics about the device and program that we created, everything was built in Python using the OR tools library, which is a linear programming or mixed integer programming solver, and with an i7 core processor and 16 gigabytes of RAM. So first, to create our data set, we need to define how we're going to generate our profitability maps. So our definition of profitability includes the profit of the field, which is calculated by taking the total revenue minus all the sources of cost that the field is subject to. And this variation of the equation was modified by the initial version proposed by Massey et al. In 2008. And in this equation, we add more categories that we try to isolate. So in the future, we'd like to be able to look at all these different categories and maybe see how they influence the total profit. And to calculate the revenue, you in most cases use a yield map times the price of grain, and you add the insurance returns, and all the costs can include things like fertilizers, herbicides, labor, etc. So our data set included one field with a range of data from 2016 to 2021. And we had to, for this particular experiment, to apply the integer linear programming method, we need to restructure the field so that it's within a rectangular format. So the data here is a symbolic version of the field, where we have a 10 by 10 grid, and each pixel in that grid represents a region of 100 meters squared. So to give you an example of what the real data set really looks like, so this is the same field that we're looking at. These two are the same, but in this case, we can see the different years of data. So there is change as you look at each isolated year, and we extract like a small region of that to run the algorithm with. So for our results, what we did is that we tried to determine the number of zones that were generated by running the algorithm 10 times. and to see what was the output. So in this case, and I have all the parameters and constraints of the experiment marked below. So in this case, we can see that the mode, which is the most reported number of zones from, the most commonly reported number of zones changed according to the year. And in some years, it was mostly constant within as you would rerun the experiment. Whereas in other circumstances, it did vary a little bit. So there was different configuration proposed depending on the number of times you ran the algorithm. And an interesting thing that we noticed by using multi-year data, so in this case, we don't look at a single year at a time, but we actually combine multiple years together and take the mean of the two. So so here, what was interesting is that there's less variation in the number of zones generated. So it means that as you look at more and more data, in a sense, it's the field kind of has this configuration that kind of remains constant, except in the year 20, when we added the 5th year. That was a little bit unexpected, but we can probably, I'm not too sure why at the moment. Maybe if I went back and looked more at this kind of, actually, if I do look at it, I can see that these 2 years were kind of low. So here we add another low year, these 2 years had a higher profit and compared to all the ones in between. So that probably influenced the final decision, just as a little guess. And if we look at the output configurations, for example, here is one that was generated with the data from 2018. So we had 4 zones shown here, and we have one large zone in the middle. So the data from this year was pretty flat. If you look at the range on the side, this had the shortest range out of all the years, from about +7 to -7, whereas the other ones would range from about +20 to maybe roughly -10. And here's another example of an output configuration that was generated. So we see that the zones don't really cover the entire field, but they do kind of have more of a, let's say, they don't cover the entire field, but we can see that like there is a kind of division between the different regions. And for future work, we'd like to, so this was a very preliminary example here using, using the data of the field kind of placed in a 10 by 10 matrix. But for future work, we'd like to work on determining a more appropriate representation of the data which would allow us to run the algorithm on an entire field. So maybe we could potentially run it on multiple rectangles and combine them, or maybe do something like a max pooling to take only the real, like to let's say dampen the signal that we get in the yield map. Or we could also work on a version of the algorithm that could function on a non-rectangular field, which would be pretty novel, considering all the literature using this method in the context of the limit of making management zones was use a rectangular field. We'd like to continue on our elaboration of the method by adding a constraint to prioritize the creation of zones that are more homogeneous. And another interesting and novel thing about our data set is that we actually have 60 fields which have 4+ years of data. So this type of method is usually applied to a single field in one experiment. And because we have such a vast amount of data with different producers and different locations, it would be really interesting to see if this algorithm is applicable on the large scale, and the different types of challenges that can come with trying to use it in that sense. So, and finally, the whole goal of this is that profitability maps and digital agriculture can help to define management zones that are dedicated to precision conservation. So what does this mean? This means that if we look at, for example, at the series of profit maps that I have here, we can see that on the field, there are regions that constantly remain negative in terms of profit. So the farmer is investing in fertilizers, herbicides, treatments to grow on this field, but something there is preventing it from growing. So in this case, what we would want to do is to create what we call potential set-aside land. And Etienne also talked about this earlier this morning. But we want to take those regions that are not producing and convert them so that instead of wasting our resources on them, we can propose a new type of management strategy where we can regenerate the soil and better make use of that land. So this is the whole goal of analyzing those series of profit maps. So in conclusion, sorry, I need to breathe because I'm speaking very fast. Profitability maps enable a spatial representation of a field, which is in dollars per unit area. So this is unique in a sense where you can look at different types of crops, different types of management practices, different years, and efficiently compare them to each other. They can be used to normalize data between fields, producers, and years. And multi-year profitability maps can depict the performance of a field over time and under different circumstances that may have uncertainties. And we can derive rectangular management zones using an ILP algorithm with both single-year and multi-year maps. Depending on the initial representation that we put into the model and the constraints, the rectangular configuration will change. But we need to focus on determining a method that can be applied over a large selection of fields, which we can use at a large scale to really see the applicability of this in practice. So with that, I will conclude my talk. I would like to thank my supervisors who helped me with my presentation, Dr. Etienne La, Dr. Abdoulaye Diallo, as well as Dr. Vladimir Reinhardt. And I would like to give a special acknowledgement to Edith Fallon, who is she is an agronomist at AFC who helped me to go through my profit data as well as identify the different categories that were important to isolate in the equation that I was using. So thank you very much, and I'll take your questions.
Thank you very much, Amanda. That was a very interesting talk. Any questions for Amanda? We have time for maybe one question. Yes, Haida over there.
Thank you, Amanda, for your presentation. Very interesting. I would like to maybe, if you go to your slide 10 when you're presenting your data set, I was just wondering if you could remember one of the biggest challenges in gathering the data set together, or some of the biggest challenges, or what you face, because we talk a lot about not having enough data to do our predictions and all. So if you could explain some of the challenges you faced.
Yes, absolutely. And that's a very good question. So in terms of this project, we were actually very lucky because we have a very large data set. We have a data set of initially, we have about 118 fields that are usable. This includes not only yield data, but also economic data like revenues, costs for each producer, each farm. And this yield data doesn't come in the same format for every farmer when you take it for them, right? So there's a whole standardization process that needs to be done. There was geospatial transformation needed to be done to make sure all the maps were in the same, let's say, spatial resolution or unit. So there was a tremendous effort of data cleaning and data preparation that took about 3 to 4 years to actually have a data set that was ready to be used. And even after all that, it took me about a year to understand all the different variables implied, what is important, what is not, what do certain variables mean? Are they worth keeping if we don't have them for one farmer, not for another? So there is a huge challenge with data comprehension and understanding that took place. But once that was completed, obviously now we have this very unique, very spatially diverse and time and temporal, a huge temporal range as well. So I think that there will be super interesting conclusions taken at the end of this project when we get to really explore all those in more detail. You're welcome.